Hello students, this is your Professor Dr. Mink, and welcome to the first lecture for CSC240 Computer Organization. I've taught this course many times. In fact, it's one of my favorite courses to teach. We're going to delve into the inner workings of a modern computer. So, with no further ado, let's get started. Here's a brief overview of what we will learn in this course. Before we get into programming in machine language or assembly language, we need to learn how to represent all kinds of information in the format a computer processes, and that is ones and zeros, binary. We will also learn how transistors, the smallest building block of an electronic computer, are used to build digital circuits that store and manipulate ones and zeros. How a special kind of digital circuit makes it possible to orchestrate the actions of those circuits. In other words, to execute instructions. And ultimately, that will lead to the definition of a high-level model of a modern computer. We will learn to write a sequence of instructions that perform desired tasks. In other words, we will write programs in machine language and assembly language. Machine language is abstraction level 0. And assembly language is most likely the only low-level language you will have been exposed to at this point in time. How to structure, store information in ways that facilitate our tasks. And we will also learn how we get information or data into and out of the computer. Our plan is to guide you to an understanding of the entire system. And in this course, we will begin describing it from the bottom up. Now, given the sequence of courses in our computer science degree, you've already learned a high-level programming language. You've learned to use a computer from the top down. You started by using its most powerful abilities. Now we're going to flip the script and describe it from the bottom up. And the bottom up is the processor processing a single instruction. That is abstraction level 0. There are two recurring themes throughout this course. One is abstraction. Abstraction is a productivity enhancer in that you do not need to understand or worry about implementation details. The example I always give in our structured programming class is that you can drive a car without knowing how the internal combustion engine works. Or to take it even further, you don't even need to know what kind of engine the car has. You simply need to understand how to interface with the vehicle, and that is the steering wheel, the gear shifter, and the pedals. In fact, many cars now do not have an internal combustion engine. They have an electric engine. Okay? And this works until something goes wrong. So it is important to understand the components and how they work. So abstraction is the first very important theme in this course. And the second is hardware versus software. And it's not either or. Both are components of a computer system. Even if you specialize in one, hardware or software, you should understand the capabilities and limitations of both. Now, we're not going to teach electronics in this course, but it's probably the course in a computer science degree that takes you closest to the fence between electronics and computer science. Big idea number one is the concept of a universal computing device. That states that all computers, given enough time and memory, two very, very important constraints. Given enough time and memory, all computers are capable of computing exactly the same thing. That means a PDA, a workstation, supercomputer. Now, let's back up a little bit. Enough time and memory are very important constraints. Sure, if you have a computer that can process a certain program, but it takes 10 days, is that really relevant? Is that useful? So memory and time are two very important aspects of computing today, especially since human beings are an impatient crew. They want things now. They want things quickly. So keep in mind that yes, all computers, given enough time and memory, are capable of computing exactly the same thing. But those two constraints are critical to performance. If you haven't watched the 2014 movie called The Imitation Game, you absolutely positively have to as a computer science major. It's about Alan Turing and his role in decoding. Well, I'm not going to give up the story. Alan Turing wrote a mathematical model of a device that can perform any computation, and he wrote that in 1937, and it's been coined as the Turing machine. And this machine, as theorized by Alan Turing, who is a mathematician, has the ability to read-write symbols on an infinite tape and state transitions based on current state and symbol. And every computation can be performed by some Turing machine. That was Turing's thesis. So we're going to talk a lot about Turing-capable machines. And there is a video link in this slide or in this video, and I'll also place it in the Canvas timeline that I'd like you to watch that describes the Turing machine. So the universal Turing machine is a machine which can implement all Turing machines. That is, it is also a Turing machine. Inputs data plus a description of computation. And in this example, U is programmable. So it is a computer. Now remember, he wrote this thesis in 1937. It predates any actual physical computers. Okay, it is a theoretical concept that really describes all modern computers. So a computer is a universal computing device, a Turing machine. Very quickly in this course, we will embark on a brief description or discussion of circuitry, from transistors up to logic gates. Here's a picture of one of the original, I call them Wintel. It was an Intel 8080A processor, and it had 32K of RAM. 32K of RAM. Think about that. Here we have the actual central processing unit, the original 8088. And as you can see on the chip, it was patented in '78 and again in 1983 by Intel Corporation. And here is the original IBM PC, personal computer, which coined the term PC, which we still use today. My high school had one that they got through a grant, and it was used by the computer club. So once again, we're going to move from theory to practice in this course. And to start with, in theory, a computing device, a Turing machine, can compute anything that's possible to compute. Now, for the caveat, the really important caveat, given enough time and memory. These are very significant constraints. Imagine, well, I have a paid Weather Channel app. It's the premium on my computing device that I carry around in my pocket. Some of you call it a smartphone, but it's so much more. And can you imagine if to get a weather forecast, it took 7 hours for that process to finish computing? How useful would that be? Not very. In practice, solving problems involves computing under constraints, time, cost, and power. So when you talk about weather forecast, next frame of animation, those are time constraints, cost, cell phone, automotive engine controller. Imagine if the ECU in a car cost $50,000. Just one component in a car that you would purchase maybe next year. Power. Cell phones, the processors in a cell phone or a smartphone, okay, have to be extremely efficient. Imagine if your battery life was about 30 minutes. How useful would that be? Hopefully you start to understand the importance of these constraints as we design computing systems and programs to run on those computing systems to meet real-life requirements. Let's just talk about the programming prerequisite for this course, which is structured programming CSC121. We would take a problem, convert it to an algorithm, and then translate it to a programming language. We were coming from the top down. Okay. Big idea number 2, transformation between layers. Okay. Problems translated to an algorithm, written in a programming language for a specific instruction set architecture that requires a certain microarchitecture that is made up of circuits and ultimately devices. Well, so in the prerequisite course, you spent a lot of time in the top 3 layers, problems, algorithms, and languages. In this course, we're going to have a brief overview of devices, the circuits made up of those devices, the microarchitecture, but we're going to spend the majority of our time in the instruction set architecture for this particular processor. And we have a fabulous simulator called the LC3. If you had me for the prerequisite course, you should remember the term top-down design, also referred to as stepwise refinement, and it's how we solve a problem using a computer, which becomes a systematic sequence of transformation between layers of abstraction. So we have a problem, and so we choose specific algorithms and data structures, typically referred to as software design, translate that into an algorithm, then we express that algorithm using a programming language. And so in the prerequisite course, we took programming C++. Some of you may have programmed in Python. There's a whole host of languages that you could express the algorithm in. And then we compile or interpret the high-level programming language to the machine language. That's the focus of this course, is to present a very popular legacy machine language. Key term is ISA, or instruction set architecture. That refers to the instruction set, the actual instructions that the processor can perform. And you'll be surprised to see how limited that list is and how much we can compute with such a limited list of actual instructions. And then the architecture in instruction set architecture refers to the microarchitecture, the physical electronics that support the specific instruction set, a logic circuit design, gates and low-level circuits used to implement components. And the microarchitecture is made up of specific circuits that are a compilation of very, very simple devices. Once again, the problem statement is stated using natural language. The last time I was paid as a programmer, I received a work order that came down through an IE, industrial engineering department, planning department, and many of the instructions were stated in natural language, in English language, and it was my job to convert those to an actual program that would run on a specific device, machine, etc. Okay, and one of the problems with the problem statement is it may be ambiguous and imprecise, so we need to translate that problem statement into an algorithm, a step-by-step procedure guaranteed to finish, that is characterized by finiteness, definiteness, and effectively computable. So that's a big part of the process, is reducing or eliminating ambiguity and imprecision from the problem statement as we translate it to an algorithm. And then that gets expressed, the algorithm gets expressed using a high-level programming language, or in some cases a low-level language. That's not done very much anymore, but it still can be the case. And then typically an interpreter, compiler, linker, etc., various pieces of software are used to translate that high-level programming language into a machine language that fits the ISA, the instruction set architecture, okay, that will run on a certain instruction set architecture. It specifies a set of instructions that the computer can perform, the data types that the instruction set architecture can handle, and the addressing mode. And we're going to get into every single facet of each of these levels in great detail. So if any of this is confusing, obviously reach out to me if you have specific questions. But trust me, we're going to drill down on all of these topics in very significant detail in this course, and have fun doing so, I promise. So to continue, the microarchitecture is the detailed organization of a processor and its implementation. And there can be different implementations of a single instruction set. So there is not just one architectural solution to fit a specific instruction set. So to elaborate, during the processor design phase, the designers determine what set of instructions the processor needs to be able to complete. And then the hardware designers go about designing the electrical or electronic architecture to perform those instructions. And that includes logic circuits, basic operations to realize the microarchitecture. And you should know there are many ways, different ways to implement a single function, such as addition, or a logic function such as or nor or not. Okay? And the actual devices, the properties of the material, the manufacturability come into play. Now, miniaturization has been a thing forever in computing. And we keep on getting smaller and smaller and smaller. And we're going to talk a little bit about Moore's Law in this course, but miniaturization is really, really important. Imagine if you had your smartphone and it could do all the things that you needed to do, but it weighed 10 pounds and it was 2 feet by 2 feet. Not very practical. Before you panic at this diagram, we're just starting to scratch the surface. We will have a very detailed explanation, many lessons on logic circuits. So don't let these logic symbols frustrate you at this point in the course. So here we have some basic logic circuits and the symbols that represent those. First is a not, and then you have the truth table. Not is a unary function, uni as in unicycle, okay? So we have A is the input, C is the output. Unary, one single input. Not turns a 0 into a 1 and a 1 into a 0. It negates. Okay, the second is and. And is a binary logic function. So you have two inputs, A and B. Both A and B both need to be high or 1 to yield a high or a 1 on the output. And there is the associated truth table on the right-hand side. And then we have an OR gate, an AND gate, and a NOR gate. And once again, I'm not going to go through each of these in detail at this point in time. We're just explaining where we're going. And when we get there, we will spend significant time on the details. There are many moving parts on this slide. And it represents the choices at each level of abstraction. And we're going to spend the majority of our time in the level that has PowerPC, Intel x86, Atmel AVR. That would be the processor, the instruction set below it, the instruction set architecture, the logic gates, and then the actual devices, CMOS, bipolar gas, etc., that are used to build the circuitry necessary to support those. And of course, right above the instruction set architecture is the high-level programming languages, and then the software design components are at the very top of this hierarchy. Here's how we will proceed through this course. I'm moving a couple topics around. We may cover data structures before I/O. Obviously, I'm rebuilding this course, so just keep that fluid, if you will. Bits and bytes, how we represent information using electrical signals. Digital logic, how we build circuits to process information. Processor instruction set, how we build the processor out of the logical elements, and what operations or instructions will we implement. That will be the instruction set. We'll get into assembly language programming. How do we use a processor instruction to implement algorithms? How do we write modular, reusable code, subroutines? How does a processor communicate with the outside world? That's I/O. Data structures, how do we structure, store information? And last, we'll just touch briefly on C programming, C++ programming actually. How do we implement high-level programming constructs? That's the end of the lecture for Chapter 1. Let's get started. This is really just a soft landing. Another analogy, I'm a swimmer. We're in the shallow end of the pool, right? We're going to get right into the deep end quickly after this chapter. So buckle up, my friends. Have a great day. Thanks for watching this lecture. You know how to get a hold of me.